that is a useful thing to know. That's really, really nice, right? Because that means if you can find continuous functions from 0, 1 into some wacky space, the image is connected, right? Let us move on. The next definition, a little bit more geometrical, I suppose. A topological space is pathwise connected if given any 2 points x and y and x. So we say pathwise connected. So sometimes I will just give this as the definition of connected in previous courses. Pathwise connected if for any 2 points x and y in x, there exists a mapping alpha from the unit interval 0, 1 to x such that alpha of 0 is x and alpha of 1 is y. Of course, we call such an alpha a path. There are tons of really cool, simple things you can prove about path-connected spaces. Here, before I get, we've been lemmaed and example pseudo example / lemmaed to death at this point. Let's look at an example. How about if I look at x equal to, I don't know, any vector space over the reals, let's say, just for the sake of being concrete. If you take 2 points in that vector space, say x and y, in the vector space, right? Then I can construct a path for you. Alpha of t is just equal to x plus y minus x times t. I think I was supposed to say that the mapping was continuous. Did I do that? That was a continuous mapping alpha. That's kind of important. Sorry about that. You can see why we want that in view of the theorem right above, right? The idea is that, the image, if this is a continuous map, right, we at least get that the image of that is some kind of continuous subspace inside the space by the previous theorem, right? It's a continuous subspace at least. So, is this a continuous map? I guess it depends on what the topology of the vector space. Let's suppose that the topology of the vector space is the usual one. Talking about a finite dimensional vector space, right? So we can give it basically the metric topology. We proved, or we should prove, or we will prove, or we won't, I don't know. Anyway, all of the metric topologies that you can induce from the different norms are equivalent. They induce the same limits even in this context. So it doesn't really matter which one, if it's a finite dimensional vector space. Anyway, the point is, however you construct your notion of topology, that is a continuous map. And those points are arbitrary. And you can easily check alpha of 0 is x, and alpha of 1 is x plus y minus x, otherwise known as y. So there you have it. Any vector space is path connected.
Didn't you talk about something like that when we were in 101?
Yeah, I think we talked about connected a little bit last semester in Redland. Now you can get greedier than this. You can look at a convex space. So if you have just x equal to some convex space, meaning that if you have, how's it go? Well, he defines it on the next page, but
isn't convex space defined by the path? The space is convex, and if and only if for any path within the space is still within the space, and it's concave if there exists a point.
I'm getting ahead
on
of
any
the
given
story
path.
here a little bit, but he says the subset A, his definition on page 66 is, I mean, say subset of Rn, just to be more specific. So it's, you know, A is subset of Rn is convex. If and only if you take the pair x and y and a, then tx plus 1 minus t times y is in A for each t in 0 to 1. So you're right, Jess. I mean, essentially, the definition of convex space is to say that this canonical trick path
Yeah.
is once more in the space again.
Yeah. And then concave is just that there exists a point in the path that lies not.
Yeah, I don't know
in
about
A.
concave. I don't have anything about concave in here. I don't remember concave. I'm not saying you're wrong, I just don't remember.
Mind if I steal your Redland books real quick?
Yeah, go for it. Here.
Isn't this similar to what we did with convex combinations last semester?
Right, yeah. I'm just saying, from the viewpoint right now, I mean, from our current vantage point, it's kind of funny because basically the definition of convex set just basically forces path connectedness. But, you know, you can think about other paths to prove path connectedness, right? I mean, convex implies path connected. Path connected certainly doesn't imply convex. For example, this space is path connected, but it's certainly not convex.
Over the topics here.
Yeah. He's like it's either Simpson hair or a ninja weapon or I don't know. So lemma 4.9, any path connected space is connected. All right. So here I'll run through the proof for you. Everybody should see this. X a path connected space. If we have A and B open, non-empty, such that the union is X, we want to prove that the intersection is non-empty. All right, so here's X. We're assuming it's path connected, and we're assuming that we've got A here, we got B here, we got X is A union B. Our goal at the moment is to prove that the intersection of A and B is not empty. All right? So what he says is, he says pick an X and A, pick Y and B, right? And then, of course, because it's path connected, there exists a path such that we go from here to here, right? So X is alpha of 0, Y is alpha of 1, right? This all we can do because what? We're assuming X is a path connected space, all right? So we're looking, we have path connected space, we have a cover, and here A and B are open, right? Not empty, all right? So far, so good? So of course, over here, I'll add this. You've got this 0 to 1, right? And so you can visualize alpha like that, right? I mean, alpha is a mapping from where to where? Alpha is a mapping from the interval 0 to 1 into, you know, x, really, right? So, what do you have? You have, you can look at alpha inverse of A, and you can look at alpha inverse of B, right? These are what? These are open subsets of the interval 0 to 1. How do I know they're open? Alpha is continuous. A and B are open. Inverse image of open sets is open, right? So, so it's got to be something like, you know, basically like this, right? And then over here, I mean, that's the issue. Right? Then what?
And their union is 0 to 1.
Right. Alpha inverse of A union B is 0 to 1 because A union B is the whole space. That's the whole domain of the path. So if alpha inverse of A and alpha inverse of B are disjoint, that's very troubling because that would mean the closed interval from 0 to 1 is not connected, but we know it is. We almost proved it today. I don't think we quite proved it. I think there was a gap in my argument. But, oh well. I do think in your real analysis course you will prove that the interval from 0 to 1 is connected. I bet you'll spend 2 weeks doing it, if I had to guess. So, I'll leave that to that course, which is after all a prerequisite for this course, even if it's a co-requisite for you. Sorry about that. So, what's that mean? It follows, right, that alpha inverse of A intersect alpha inverse of B is not empty, right?
So there's some T star in 0 to 1. It's an element of both alpha inverse A and alpha inverse B.
Right.
So alpha T star is in A and B.
Right, so that alpha, that T star you're talking about, like that point right there. And if that point, that's an element of A intersect B, which then of course is not empty, right? So then that proves that there doesn't exist a separation of X, which shows the path connected implies connected.
I've had no such luck.
Oh, it's okay. I don't think we talked about concave. We talked about convex. We talked about more interesting things. We talked about convex, what are those called? The
Convex holes.
cells,
Simplexes.
the simplexes and the complexes, the collection of these convex sets and such. And, anyway, okay, so now, and of course, what are you going to ask next once you see this?
It's the converse true.
Exactly. Is it the case that connected implies path connected? Here's another lemma. I'm going to leave that question hanging there for a minute. 4.10. It says A and B path connected. Then what? In a topological space, if A intersect B is not empty, then A union B, path connected. So basically the picture is something, it's pretty simple, right? Like, what's wrong with me? So here's X, here's A, it's connected, here's B, it's connected, right? Path connected rather, path connected. There's something in common, right? There exists one point. In fact, it could just be one point. That's all it takes, right? It's like, it's Mexico. It's the United States. Just one break in the wall. Don't worry, Trump will remove that point. He's gonna do it. He's gonna make America great again. Warms my heart. I'm actually starting to think Trump's not gonna win. Because he's been kind of petulant lately. But anyway, I digress. So if you pick a point here, X, and you pick another point over here, Y. First of all, if the 2 points you pick in the space A union B are in either A or B, you're done. Because we already know that's path connected, right? So the question is, can you make a path from here to here?
Yeah.
All you do is you pick the common point,
And you
and
can get a path in A and a path in B.
Right.
And construct a third one.
so then the question is, can you join two paths to make another path? In our current formalism, you have to take, suppose this is alpha, and suppose this is beta. Let me say this is beta and gamma, rather. These are paths, right? Can you make an alpha t, which is what? You gotta use the beta. So like we do, okay, so like
Beta of 2t.
beta of 2t, okay.
For t from 0 to 1.
0 less than or equal to t, less than or equal to a half.
5 o'clock p.m.
No, it's not. Lies, lies. Gamma of
2t minus 2
2t minus 2?
minus 1.
Minus 1, okay. And that's from 1/2 less than t less than or equal to 1, I think. Where, of course, we assume that beta of 1 is equal to gamma of 0 is equal to the point P, which is an element of A intersect B, which exists because we assume the intersection is non-trivial. And there you go. It's a gluing together of two continuous paths, which you can show as continuous. So there you have it. All right. I'm going to state without proof corollary 4.13, and then we will spend the remainder of today on madly interesting theorem. I mean, these theorems are, wow. Yeah. Okay. I hate to erase any of these things because I think they're also interesting. Well, I guess we don't need that example anymore. Fine. So here's the corollary. Following our equivalent. This is a corollary 4.13. It's a corollary to the statement that any convex subset of Rn is path connected and hence connected, as we already discussed. But following our equivalent, I is an interval, i.e. convex subset. I is path connected. Three, I is connected. What's the context here? So the corollary, the corollary 4.2, based on the stuff I just erased over there, said any convex subset of Rn is path connected and hence connected. If we apply that same idea to R1 itself, so what we're talking about here is actually intervals of real numbers. So in calculus 1, I give a rather clumsy definition of interval of real number. I just say there are 9 kinds, and I list them. Open rays, closed rays, to infinity or to minus infinity. There's 4 kinds of those. You've got open intervals, closed intervals, open, opposed, and then the whole real line. There are 9 of those. But there's a more simple way of describing all of those. Those are all convex subsets of the real line, which is equivalent to saying those are path-connected subsets of the real line, which we do sometimes use as a definition of interval in other courses, right? We say it's an interval if you can draw it on the number line by drawing your marker without lifting it, right? That's an interval. Now sometimes you have to draw for a really long time, but yeah. So there's that corollary. Okay, great. Lemma 4.16. I think if you haven't read the book beforehand, I won't ask if you have or not. This might be surprising. Let n be greater than 0, and f a continuous map from the n sphere to the reals. Okay? There exists x in the n sphere such that f of x is the same as the value of the antipodal point minus x. In other words, f of x is equal to f of minus x. In particular, f is not injective.
Wait, so f is continuous now?
Yes. It's the only kind I know about in here, really. Sorry. But you're right, I should say that, continuous. Alright, so what's the proof? He says, consider the continuous map G from the n sphere to the reals defined as follows. So we're assuming we have a continuous map F, and n is greater than 0, okay? So look at G, constructed by, what you do is you look at G of x is defined to be the difference of f of x and f of minus x, okay? So far so good. Is that a continuous function? Yeah, I mean it's the composite of continuous functions, so it's continuous once more. Assuming we know that subtraction is the continuous map on the reals. I haven't proved that in here, but take my word for it. I guess. Can't tell, you guys are kind of, we'll play poker with you guys. See here. Well, I don't know how to play poker, that's part of the reason. Good way to not play poker is if you don't know the rules. Let's see here. As n is greater than 0, the n sphere is connected. All right. That's the part I skipped over, but can you see how to prove it? It's what I wrote over there, but there's a little bit more you have to prove, right? It's not immediately obvious that the path image, if you take 2 points in the n sphere, right? You need to prove that the, oh wait a minute, is this the skin? Oh, I gotta use like a great circle kind of thing. But the point is, you can construct, using great circles or whatever, between any 2 points, some kind of, I want to do this, but that's not relevant, sorry. Like that. Oh, now it's like a Baymax. So, I have no regrets. All right, so anyway, in fact, you can prove the n sphere is connected. That would be a fun homework problem. You could come up with formulas to do it, right? Not something I could do, not something super, really topological and clever, just a formula. So anyway, the point is, if this is connected, that implies that G of Sn is what? It's a continuous image of a connected set. This is also connected, right? Remember we proved that if you have a connected set and a continuous function, the image is again connected. But this is a connected subset of what? Of the reals, right? Therefore, what? It's convex. All right? So what he says then is he's like, okay, so pick any arbitrary point in Sn. Y, an element of Sn, right? Then G of Sn contains, he says, G of Y and G of minus Y. Is that immediately obvious to you guys?
Yeah. Since y, well, I mean, because y and minus, like y an element of Sn, I think implies minus y an element of Sn.
Right. Oh, right.
Since it's an element of the domain, I mean,
Oh, okay, yeah, this is not a deep thing.
yeah.
Right. Agreed. So then what? Also the convex combination. And the convex combination of 1/2. So we can look at 1/2 G of Y, right? Plus 1/2 G of minus Y, right? This is a convex combination, right? 1/2 plus 1/2 is 1, so that some of the coefficients in the sum are 1. That's what it means for a convex combination. That's a convex combination. By definition, a convex combination. But what's that? Oh, this is cool. You know what this is? This is like an actual use of my stupid every function is a sum of even an odd function comment. But it's that algebra, but doing something really interesting, I think. See what happens here? So that's just definition of G, right? G was this plus this. So that's that, minus and minus is plus, and what happens there?
Streams into
Oh, yeah, what is it? That's just what?
f minus f of y. F of y minus f of negative y.
No, I think it's just f of y.
Oh.
Yeah, it is. Dana's right.
But can you guys believe what I wrote? Or have I made a typo? Remember, the definition is minus. So with that adjustment, what is your answer? I would point out to you, this guy cancels with that guy.
Well, it's just 0.
This one. Yeah, it's 0.
But g is always 0, regardless of whatever it is, right? Topology. Because if f of x
Oh,
is
no,
equal to f of
this
negative
is,
x,
you're right, this is identically 0, but this is just for, that's just for this point y. I mean, we're studying this, we're adding y and minus y. There are lots of other points that are, this is a very particular convex combination we're looking at. I mean, it's not. So what's it say, though, is that 0 is an element of the image, right? So what do you got? You got, so there must be what? There must be x what? There exists x in where? In Sn such that what? G of x is equal to 0, right? And what does that tell you?
There exists x such that f of x is equal to minus x.
So let Y be a connected topological space, F a continuous map, continuous surjection, such that the inverse image of any singleton is connected. Then if F is open or closed, then X is connected. Let me read that again. So if you have a continuous map, which is onto a space, right? And you have, here's Y. And if you take any Y in here, like this, and you look at the inverse image, or sometimes we'll just write not curly brackets, just F inverse of Y. So that the fiber of Y in X, then what? And suppose that every such inverse image is connected, all right? Then he says if F is open or closed, then X is connected. So this is another, and the proof is here. I'm not going to go through it. Another thing we have, just to wrap up section 4.1 for today, the product of two connected spaces is connected. So you can use it's an argument by the projection, continuity of the projection, and this lemma 4.18. So these go together to prove that the product. The reason for that lemma is to prove that the product of connected is connected. All right. And that brings us to section 4.2, which I'll describe to you briefly, but I won't prove anything from today. So section 4.2 is on connected components. So it turns out that basically you can take any topological space, right? Oops. And you can just start picking points, right? And you can find some sort of maximal set around that, which is connected and contains that point. This is called the path component of that point. And you can keep doing this. You know, eventually you find some maximal subset that is connected and contains a point. Pick a point outside that. You'll find some other maximal set, which is, in my picture, doesn't do it justice. Right? I mean, here's a better picture. The topological space is this. Right? It's just these disconnected pieces. Those are the path components. Oops, I erased one of my components. No. And so any topological space can be written as a union of these path components. And every path component is going to be both open and closed, I think. Well, wait a minute. Now I'm getting overboard. Going overboard. So you're so well, he says you can denote by Cx the union of all connected subspaces containing X. All right. Then it's an arbitrary union. Then Cx is a connected component that contains X. So I mean, this is basically the idea. You take this. We use closure. We use this arbitrary, like this intersection of all closed set, which contain a set as the closure of the set. This is kind of complementary to that idea. We take the union of all connected sets, which contain a particular point. Then that gives us the connected component of that point. So this is kind of dual in that regard. And like he says, every topological space is the union of its connected components. Each connected component is closed, and any point that's contained in one, and each point is contained in one and only one connected component. Lemma 4.28, every point in a topological space has a connected neighborhood. The connected components of X are open. Then section 4.3 is on covers, which is a really short section. And then that leads into section 4.4, which is on compact. So hopefully next time we meet, I can wrap up there's not much more to say about connectedness in here. The connected component stuff is pretty simple. I think this is the very interesting, this is the interesting level I wanted to get to, because this is actually a statement about something that doesn't seem to have much to do with what we're talking about, right? All of a sudden, talking about connectedness of intervals and such, and all of a sudden you find this fact, this kind of deep fact about mappings from spheres to real numbers. That's the kind of thing topology is, this surprises us with these sorts of theorems from time to time. Like that Perrin-Frobenius theorem I never covered last semester in advanced. There's a few things. These fixed point theorems are very interesting. All right, well that's all I have for you guys today. I will shut up and let you go. Sorry we got started late again. I will eventually start on time and end on time. It's gonna happen.